Hello and welcome to the Daily Space for Friday, August 17, 2018. I am your host, Dr. Andres Plazas. As always, we're going to bring you a roundup of today's news from space and astronomy. So today's first story has to do with the Hubble Space Telescope and astronomers using the ultraviolet vision of this NASA facility, NASA and ESA facility, the Hubble Space Telescope. They have captured one of the largest panoramic views of the universe, where you can see regions of star formation in the distant universe. So this is a field that features approximately 15,000 galaxies, and about 12,000 of them are forming stars. And the ultraviolet light now has allowed us to get this picture that is in a way complementary to other type of data that Hubble has been able to take in the past, such as infrared and visible light data. Not only from the Hubble Space Telescope, but also from other space and ground-based telescopes. So this image actually let us take a look at the very distant galaxies that can only, at the same time, the very distant galaxies that can be looked at only in the infrared light, and closer galaxies that can to be seen in a broader spectrum. So when we want to look at the light from very distant star-forming regions in remote galaxies, actually, we have to look into the infrared. Even though these galaxies, the light from these star-forming regions started in the ultraviolet, due to the expansion of the universe, there has been a shift in the wavelength of this light into the infrared wavelengths. So by comparing these images of a star formation in the distant and in the nearby universe, using both infrared and ultraviolet, astronomers can have a better understanding of how nearby galaxies grew from small clumps of the hot and young stars a long time ago. And of course, because the Earth's atmosphere actually filters out most of the ultraviolet light, the Hubble can provide some of the most sensitive space-based ultraviolet observations that are possible. So this is actually a program called the Hubble Deep Ultraviolet Legacy Survey, and it extends and builds on a previous Hubble multi-wavelength data called the CANDLES Deep, and CANDLES stands for Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. And they were pointed into a particular field that is called the GOODS field, the Great Observatories Origins Deep Survey field. So we have all these funny acronyms that you find all around in the papers, but they're just describing us what the fields are and what we're doing in those fields. And in this press release, the Space Telescope Science Institute points out that this is a mosaic that is 14 times the area of a previously released field in the same wavelength called the Hubble Ultraviolet Ultra Deep Field that was released in 2014. So yeah, that was the first story of the day, telling us about this new type of data available in the ultraviolet, and just a personal note for when you do research. This type of very deep fields taken by the Hubble Space Telescope are very important. For example, in my own field of research, which is weak gravitational lensing, we frequently use these deep fields taken by the Hubble Space Telescope, and we are interested in measuring the shape of galaxies from ground telescope, but we use this type of images from the Hubble Space Telescope that have better resolution, that are actually deeper, like that is to say they have more integration time. We use them as a more truthful representation of what we can find of the sky. In a way, it's some sort of a truth table. And then, because of course we have a better resolution and a better way of telling the properties of galaxies using the Hubble Space Telescope than a telescope on the ground. So The only drawback with respect to that is the field of view of the instruments of the Hubble Space Telescope, of course, is way smaller than when you can build with one of the hundreds of millions of pixels cameras that we can get on the ground. So just a side note to point out the importance of this type of deep fields, and especially in addition of what the news were telling us, that you can have a complementary information between the ultraviolet and the infrared to find about the star formation. Um, it is always great to have all these fields with very high quality from the Hubble Space Telescope to do research, of course, with ground-based telescope. Um, and the second story of the day has to do now with Mars, and this is some news coming from JPL regarding the Opportunity rover that, as we know, it has been silent since June 10th because there was a dust storm cycling the whole planet that has cut off all the solar power of the rover. So scientists recently started to think that this global dust storm is decaying or waning, and that is to say that more dust is falling out of the atmosphere than is being raised back into it. And they hope that the skies might soon clear enough for the solar-powered rover to recharge and attempt to contact us here on Earth. So, well, no one will know how the rover is actually doing until it actually communicates with us. But the team, they know that actually there might be reasons to be optimistic, right? They have performed several studies on the state of the batteries before the storm and the temperatures and the location. And well, they know that because the batteries were in a relatively good health before the storm, there's not likely to be a lot of degradation. And but then the questions that they ask is like that we can ask is what will the engineers at JPL could be looking for when like what kind of signs they would be looking for to assess that the rover is actually trying to communicate with us, or what kind of parameters we should be actually be paying attention to. So one of the main parameters has to do with the opacity of the storm, which maybe from previous press releases you may remember that people call this parameter tau, which the significance of this parameter is like the higher this tau parameter is, the less sunlight you have available. No, it's a measure of how thick or how opaque the atmosphere is due to the dust storm. So just to give us some numbers, the last of this parameter, the last number of this tau parameter that they measured on June 10 was of about 10.8, which we should compare to an average tau that you usually should get of 0.5 or something like that when under usual conditions. So JPL engineers predict that the Opportunity will need a tau of less than 2.0 before the solar power batteries will be able to be recharged. Also, scientists are actually listening or paying attention to any signal that might come from Opportunity by monitoring the Deep Space Network, which is communicates between the planetary probes and the Earth. So there are three types of sites on the Earth, and there you have all these giant antennas that are communicating with all these probes in deep space. One of them is in Goldstone, California, the other one is in Madrid, Spain, and the other one is in Australia, I think in Canberra, but I'm not sure. But the point of having this on different types of the points of the Earth is to be able to communicate with all spacecraft at all times, regardless of the rotation of the Earth. And yeah, so they actually are listening to any wake-up call, and they're monitoring this every day. They record any radio signal that could come from Mars and try to see if Opportunity is trying to communicate with us or not. Then there is another parameter to take into account, which are like what they call the faults mode or the defaults modes. And when the opportunity experiences a problem, it can go into what they call the fault modes, where it actually automatically takes some actions in order to keep its health and in order to be safe again. They just basically go into safe mode. So the engineers actually they predict that probably opportunity is right now in three key fault modes. So the first one is the low power fault. The engineers have assumed that the rover went into the low power fault mode shortly after it stopped communicating on June the 10th. So this is a mode that causes the rover to hibernate, and it is designed that it will wake up at a time when there's more sunlight to let it recharge. So there is another fault that is called the clock fault, and it's critical to operating while in hibernation. Um, because it's actually the internal clock of the rover. So if the rover doesn't know what time it is, then it doesn't know when it should be attempting to communicate. And well, the rover could also use some environmental cues, like maybe an increase in the sunlight or something like that, in order to make inferences about what time it is. But it's important to have this internal clock in the rover, of course. And there is another key mode that they might be looking at that is called the Atlas fault, which it means that when the rover hasn't heard from Earth in a long time, it can go into this mode, and it is a warning that the communication equipment may not be functioning. So the rover, if the rover hasn't heard from the Earth, then it starts experiencing this mode, and then it begins to check the equipment and tries different ways to communicate with the Earth. But then, what happens if they hear back from the rover? So, well, there could be maybe a lag of several weeks before a second time, because the scientists in the press release actually compare in keeping the proportions. Like, it's like a patient coming out of a coma or something like that. Gonna take some time to fully recover for all the equipment to be able to have fully functioning communications with us. And yeah, well, the first thing that they have to do is to learn more about the state of the rover, and they will ask for a history of the rover's battery and the solar cells, and then measure the temperature. Then, if the clock has lost the track of time, it will be reset. And the rover, of course, would take pictures of itself, like, we have seen these selfies on social media of the rover to see whether there might be dust, a line on sensitive parts, or maybe in some other components of dust affecting the joints or other components of the rover itself. Um, so yeah, well, then even then, engineers point out that even if we check all these parameters and then we hear back from opportunity, there is a real possibility that the rover actually maybe won't be the same, and it won't work as it was intended to, because a consequence of this state that it's going through. It could be that the rover's batteries could have discharged so much power and stayed inactive so long that their capacity is reduced by now. Or if those batteries cannot hold as much charge, that it could affect the rover's continued operation if they're not working as they were supposed to. And it could also mean that if you have this energy draining behavior, like for example, like running the heaters during winter, it could cause the batteries to actually just start failing as well. Um, yeah, but so, well, in general, the engineers conclude saying that the dust it's not usually a lot of a problem, but an previous storm have actually put dust on the camera lenses, and most of it has been shed off out of time, and any remaining dust that you can find in a camera or in a lens could be calibrated out. So yeah, there are certain parameters that we need to take into account. There are certain reasons to be optimistic about what to expect, but at the same time, of course, engineers and scientists are prepared and to take action to try to recover the functionality of the rover as best as they can. And for the last story of the day, we're going to talk about some of the oldest galaxies in the universe. This is a study in which astronomers have identified some of the earliest galaxies in our universe. So this is a team from the Institute for Computational Cosmology at Durham University and from the Harvard Smithsonian Center of Astrophysics. And they actually have found um, evidence that points out that some of the neighboring galaxies of the Milky Way, the dwarf galaxies of the Milky Way, actually are amongst some of the universe earliest galaxies in the universe. And the scientists in the press release actually point out something funny. They say this is something equivalent to finding the remains of the first humans that inhabited on the Earth, like right laying in our backyard. So the research suggests that galaxies, some of them include like Tucana 2 and Ursa Major first. They are in fact some of the first galaxies that have ever formed, about 13 billion years old compared to what we think is the time of the Big Bang, 13.7 billion years old. So they link this to the epoch of recombination, or to the early epoch of the universe. So when the universe was about 400,000 years old, the very first atoms formed, and then these were hydrogen atoms, and this is one of the, of course, the simplest element it's actually the simplest element in the periodic table of elements. And these atoms they collected into clouds and began to cool gradually and settle into small clumps or halos of dark matter that emerged after the Big Bang. So during this cooling phase, there was not anything illuminated in the universe. So this is called the cosmic dark ages. It lasted about 100 million years. Then eventually, these gas that cooled down and inside these halos of dark matter started to become unstable, and little by little they started to form stars. And these are the objects that are the very first galaxies ever to have formed. And with the formation of the first galaxies, then the universe burst into light. And then that actually brings us to the end of the cosmic dark ages, as the universe was again reionized. And so the um, the first so these researchers actually identified two populations of satellite galaxies orbiting the Milky Way, and the first of these populations was a very faint population consisted of those galaxies formed during the cosmic dark ages, as I was just saying. And then the second type of population that they found amongst the neighbors of the Milky Way was a slightly brighter population consisting of galaxies that formed hundreds of millions of years later, once the hydrogen that had been ionized by the ultraviolet radiation emitted by the first stars was able to cool into more massive dark matter halos. And the researchers also point out that in a remarkable way, the model of galaxy formation that they have developed in other studies actually agreed perfectly with the data. And then this allowed them to infer the formation times of the satellite galaxies. And they also point out, is another of the conclusions of the study, that this is a model that is consistent with the standard model of cosmology, what we call the lambda cold dark matter model, and the lambda standing for a cosmological constant as dark energy. Yeah, okay, so these are the three stories that I wanted to share with you today, and I'm gonna now look at your comments and say hi to everyone, and see what you guys have to say. So, hello, Fenrig, fellow Hulum, Widow B. Hello, UHE. Hello, Fenmil, Astro YYZ. Hello, Larry. Hello, Graham. Hello, Honey. How far can you see with good gravitational lensing? Is asking Honey. So usually in this type of surveys that we're doing, we actually are looking into a relatively early universe. So in gravitational lensing, we need to have something that is doing the lensing, the lens. And in many cases, this is a cluster of galaxies, and we see very elongated galaxies, and then you see what is called the strong lensing. When we want to study cosmology, we usually use as a lens the large scale structure of the universe itself, and this is a structure that has formed uh, later in the history of the universe, in the relatively early history of the universe. Because at first in the universe everything was very hot, very dense. Then everything started to expand and cool down, and things were very homogeneous. There were just these tiny inhomogeneities, and then as time passed by, these little seeds where there was a little bit more of matter than in another place, then they started to grow up into the nonlinear structures that form what we call the cosmic web. So when we use the weak lensing of the large scale structure of the universe, this is a special case of gravitational lensing, and it's a special case of weak lensing, and we call this cosmic shear. We're actually looking at the universe relatively close to our age, about 4 billion years ago or something like that, compared to the 13.7 billion years ago from the Big Bang. And this is one of the things that makes gravitational lensing very powerful, because you can test your cosmological model when the universe, let's say, when the universe is like right now in the current age, so to speak, or close to the current age, and then with an independent method, which is the cosmic microwave background, which is giving us information of the very early universe. With that method, you can also have information of your cosmological model, and then you can put together those two methods and see if they make sense or not. And then another thing that comes into my mind with gravitational lensing, not with weak lensing, but this time with a strong lensing. The cool thing is that you can use galaxy clusters themselves to work as cosmic telescopes, because gravitational lensing not only distorts images but at the same time magnifies images. It's like a lens. That's why we call it lens. So for example, one of the things that a strong gravitational lensing allows us is that we can actually see farther than we could see if the lens did not exist. So there is something called the Hubble frontier fields, if you Google that, and then you'll see certain type of galaxy clusters that produce very elongated and distorted images of galaxies that are very far away, distant in the past, and these are the very first galaxies in the universe. And you can even see little clumps of star formation within those very old galaxies. And then this gives us information about the star formation rate back in the time, which again we can compare to the star formation that we measure like now, and then try to see how galaxy evolution works. And this is another example in which gravitational lensing allows us to look very far in time. In this case, a strong gravitational lensing. Okay, that was that for it. Thank you for your question. I'm so looking forward to looking at Mars without dust, sans dust. Yes. That was a comment by Astro YYZ. Does Opportunity communicate with overhead satellites, or does it communicate directly with Earth? That's a good question. I think I'm not sure about that. I think it does communicate with a satellite orbiting the Earth, the Mars orbiter. And then that's the one that communicates with us. I don't know the details of that, but I think that's how it is. Are any diagnostics of Opportunity possible if she never signals us again? Um, I'm not sure about that. I'm trying to think of a way in which we could know more about it uh, without it signaling us, and I can't think of a way of how that would happen. So it's like, like the other one, the other rover that got that stop communicating with us, which I forgot the name. But you know, if it doesn't communicate with us, I think that is as far as I know. Then Guido says we were bound to lose opportunity at some time anyway, and if it doesn't wake up again, at least it went out in style. The most epic dust storm in the recent history of Mars. Yes, that's another way of looking at it. Like we always say, oh well, these things were supposed to last only like 3 months or something, which is the case, right? Um, so usually these missions they have a nominal lifetime of about 3 months or 1 year, something like that. But they're so well made in the end that they end up even working for years. So you can think of it as the glass half full, and think of it as from the positive point of view, and say, well, we're actually running on extra. Shouldn't have been working all this time. But then, yeah, that's so that's the way of looking at it. So shouldn't all Hani is asking us, shouldn't all galaxies by now be accumulations of smaller irregular galaxies from the beginning of time? Does that mean that the galaxies haven't had much to eat since formation? How is this different from the Milky Way? Um, yeah, about this, how this satellite galaxies actually came into be. So yes, in general, we have the picture of hierarchical formation of the large-scale structure in the universe, which is that either you can have two options, right? Like at the beginning of time, you have like a giant clump of matter that started to partitionate in smaller clumps, and that would be like the top-bottom approach. And then you have the other option, which is that from little clumps of matter, then of halos of that matter, then they started to merge into like a tree of mergers. And I evidence actually points out that yeah, it is the latter, actually, the bottom top approach, or the smaller clumps of halos merging together into um, larger halos, which in turn then turn into clusters of galaxies when the potential well of the halos draw the baryonic matter that we can see. So, but yeah, with respect to the satellite galaxies of the Milky Way, so maybe these were actually galaxies that were not part of any accretion process at those scales, and they were just maybe captured after the formation of the dominant, like in our case, in the local group of the galaxy, the dominant galaxies of the group, which are the Milky Way and Andromeda. So yeah, that's galaxies like mammals have the urge to merge. So I think, so I'm not sure about that, and I think that's yeah, these galaxies were just captured afterwards and were not part of the main merger of the Milky Way, or the other possibilities that they were actually yeah, well, I don't I don't know. I was thinking about something different, but now I realize it's not relevant to this. Does gravitational lensing cause the wavelength of light we see to be different from the normal? Can it act like a prism? No, and this is a very good point. This is where the analogy breaks with lensing. So the equations tells us that um, the effect of gravitational lensing does not depend on wavelength. So the same. This is a consequence of the distortion of a space-time by the distribution of any distribution of matter and energy in the universe. And then what the light is just trying to do is to go from point A to point B in the shortest amount of time. You can think of it like that, and this is called Fermat's principle. You can find that in optics, and in regular optics, right? And then but you do find the effects like refraction or dispersion, where the like in the case of refraction, for example, then you can see a different angle of refraction depending on the wavelength of light, and then you have a prism. In the case of gravitational lensing, you do not have this dependency with wavelength, and then the deflection angle experienced by light is the same regardless of the wavelength. And then that's why, for example, there are people who are trying to do gravitational lensing in the radio with the SCA, for example, the square kilometer array, when it comes when it starts working. But then now the challenges are not maybe from the theoretical point of view, but are from the systematical point of view. Then the what is called the point spread function and other types of systematic effects or systematic errors need to be taken into account that are different from what you can find in the optical. But people are thinking about using that information as well. Someone is going to have to go up to it and download Opis logs. Yeah, that could be a good novel or something in the future. Somebody can go there like in The Martian when the guy finds the Pathfinder rover to survive. Is the picture on a screen real or an artist representation? I think this one that says Auriga project. I don't know. It looks like an artist representation. So let me check if they have some reference in the press release. I don't see any reference from that, so it would be Auriga project. Let's see. Let's see. These are simulations. There you go, it's a simulation. The Auriga project is a large suite of high-resolution magneto-hydrodynamical simulations of Milky Way-sized galaxies, simulated in a fully cosmological environment. It is simulated with the state-of-the-art hydrodynamic movement mesh code, that's some sort of embodied simulation code, and includes a comprehensive galaxy formation model based on Illustris, which is one of the embodied simulations, one of the best ones that we have. Okay, so it is a simulation. All right, everyone. So I think we can call it a day. But I do have an important announcement to make. And next week, the Daily Space will start 1 hour later. Dr. Pamela Gay will be back with us. As I mentioned before, she will be doing it from the International Astronomical Union meeting in Europe, in Vienna, Austria. And because of the time difference, we're just gonna move it a little bit later. So so that would be 2 p.m. Eastern time, and what are the other times? 11 p.m. Pacific, 11 a.m. Pacific, and 7 p.m. London. Just to keep that in mind for next week's Daily Space. And thank you so much for watching. Actually, for watching this whole week and being with me. This has been the Daily Space, a production of CosmoQuest, created by the Astronomical Society of the Pacific. And our goal is to put science in your brain. If you like this show, please give us a follow. Follows are free. And if you want to sustain our efforts, please consider subscribing. Every bit also helps. Next up on this channel will be Dr. Matthew Richardson and Joe, probably, bringing you Astro 101. So Okay, see, the Daily Space will be back next week and every day of the week. And as I said, next week it will be just 1 hour later. We'll have Dr. Pamela Gay with us again. All right, have a great weekend, everyone. Thank you. Ciao, adios, bye bye.